Alright, so now we're going to try some examples, some situations that have to do with electric potential difference. So our first example is that in a uniform electric field, a test charge is moved from the negative plate to the positive plate. Now, if the potential difference between the two plates is 80 volts, and they are separated by 10 centimeters, calculate the strength of the electric field. Alright, so we're looking for our electric field here. That's where our epsilon. All right, I have a charge here. We have a charged field, and so we have a positive plate on the top and a negative plate on the bottom. And so our electric field, again, always flows from the positive, so it's directed down. All right, so there's our electric field, and we want to know that strength. Other things that we know, 80 volts. Yes, that's a potential difference. So let's have our 80 volts there. Okay, and we have a test charge. Here it is, little positive test charge. It's going to be moved, all right, towards going from the negative plate to the positive plate, which again has a distance of 10 centimeters, which again is no good to us. It's got to be in our standard units here, so I'll put it in meters by dividing by 100. All right, now we're looking for epsilon. We know our potential difference is 80 volts. And so if I look at my formula sheet, I check it out, I do have a formula. We have delta V that we just came up with. All right, minus sign, we have epsilon times delta D. These are actually vectors, because that's going to come into play here, because there is distances involved. Now, here's the thing, our voltage is 80 volts. We have our negative sign, our epsilon. Well, that's what we're trying to find, the strength of our field. Now, here's something, delta D. You see our field is pointing down in this situation. I could have drawn this diagram left and right, but I just chose it up and down, no big deal. But the key here is that our electric field is pointed down, but yet look at the test charge moving towards the positive plate is moving in the opposite direction. And so instead of 0.1, I'm going to put a negative 0.1 because again, the displacement, or the displacement I should say, is a vector. All right. In the end, though, these two minus signs or two negative signs are just going to cancel each other out. And then we now what do we got? So we got 80 is equal to, I guess we put our 0.1 first here in front of epsilon. And then I want to get epsilon by itself. Whoops, not 0.8. Should have a 0.1 there. Let's get rid of that. There we go. All right, so I'm going to get epsilon by itself. I'm going to divide each side by 0.1. Those divide each other out. And again, we're just looking for the strength of my electric field because I could have drawn this diagram, like I said, multiple ways. Now, if I take 80 and I divide it by 0.1, I get 800. And again, that is newtons per coulomb. But again, these two minus signs cancel each other out because, again, for delta D, I made it negative because epsilon, which again has direction, and delta D, which has a vector, it has direction. And in fact, they are in opposite directions. All right, so that's a situation where we're looking at electric potential difference. Another one, now there's a lot of background here, but I'm not going to talk about it too much here, about old television sets and how they work. But we'll get to A, because it basically explains how the old television sets work. So it says, an electron leaves the negative plate of a cathode ray tube and travels toward the positive plate. All right, the electric potential difference between the plates is 1.5 times 10 to the power 4 volts. Using the law of conservation of energy and the definition of electric potential difference, calculate the speed of an electron as it reaches the positive plate in a cathode, easy for me to say, ray tube. Assume the electron is initially at rest. The mass of an electron is, there we go, 9.11 times 10 to the negative 31 kilograms. All right, so here's what we got. So I always read the question, then go back over it. is that an electron leaves a negative plate. All right, so we got 2 plates here. Let's, I don't know how I'm going to draw it. I guess we draw a plate like this. There's our negative plate. So let's put negatives there. All right, then we have a positive plate over here. So we'll put our positives. Okay. Now, there's an electron that goes from the negative. Now, again, the 2 negatives repelling each other. So it's going to, it's like a spring that's been pushed together really tight. And now all of a sudden this electron, which again initially is at rest, I should mention, is going towards a positive plate. Now it says the potential difference between these two is 1.5. So that's our delta V times 10 to the power of 4. Now, 10 to the power of 4, let's type that into my calculator. I believe it's a 10,000, but I want to make sure. Yeah, it's 10,000. I times it by 1.5, and we end up with 15,000 volts is our potential difference. All right, now we have the mass of an electron, which is 9.11 times 10 to the power of negative 31 kilograms. It's the mass of our object. And what we want to know is what speed does it hit this positive plate? Now, again, we got to use the law of conservation of energy, is that we're going to have a certain amount of electric potential energy, and it's going to change, and so is our kinetic energy, because this electron is going from rest, speeding up, and again, those are differences there. All right, so again, we have all this electric potential energy that's stored up because there's some tension between these two. They want to repel. It's like, again, a spring being loaded up, pushed together, compressed, and all of a sudden it's released. So you're going to lose that electric potential energy, but we are going to gain that back in kinetic energy. And so we know that delta V, let's see here, we know the mass, and again, we want the final velocity. Oh, and our charge was an electron, and the charge of an electron, again, if you look at our formula sheet, oops, let's put that in blue, just like I did with the other ones. Our charge on an electron, again, is negative 1.6 times 10 to the power of negative 19 coulombs. All right, now, we just came up with a formula involving delta E and delta V and Q, where we have delta E is equal to, let's see here, check my formula sheet. We have Q1, which is the charge we're dealing with, our electron here, times delta V. Now, kinetic energy, once again, is mass times, we got Vf squared minus Vi squared. Of course, the kinetic energy, we can't forget to divide by 2. And that's going to equal 0. All right. So let's see. Now to substitute in our values. So we have Q1, which again is that, oops, let me see here, negative 1.6 times 10, power of negative 19. Our delta V, see up there, 15,000, electric potential difference. Our mass, hope I don't run out of room here, is 9.11 times 10 to the power of negative 31. Now, in this formula right in here, we have our initial velocity is 0. So what I can do here is my initial velocity is 0. Well, of 0, it's gone. So really, I don't need the brackets anymore. I'll leave that bracket there. And so I'm just going to multiply by my VF, and I'm going to have to square it. So VF is, oh, that's what we're trying to figure out. So I'll put a VF squared. Can't forget about my divided by 2 here. And it equals 0. All right, so let's see here. Well, I'm going to Let's see what's the easiest way to go here. Extend the page. I'm going to need more room. I'm going to move this massive term right here. I'll move that over to the other side because I got to get VF by itself here. So we'll move that over to the other side. I'm going to calculate. I'm going to multiply these two numbers together and see what I get here. So let's see. I multiply those two together, and I end up with, I get negative 2.4 times 10 and to the power of negative 15. All right. And that's going to equal, well, we got this term I moved over. It was positive here, but it changes sides, so it's going to become negative. Well, let's divide 9.11 times 10 to the negative 31 divided by 2. Let's see what I'm getting here. I'm getting negative 4.56. Still a very small number, times 10 to the power of negative 31. And then I got my VF squared. All right, now let's see. We're getting simpler. That's always good. We're going the right way. Again, I want to get VF squared by itself, so I'm going to divide both sides here by negative 4.56 times 10 to the power of negative 31. And what I do to one side here, I'm going to do the other. There we go. All right, so those gone. They're gone. And then let's see. So on this side here, I got VF squared. Okay, now I got to take negative 2.4 times 10 to the negative 15. It's a 15. Bad writing. And divide it by negative 4.56 times 10 to the negative 31. Let's see here. I end up with negative divided by negative is going to be a positive. And so I end up with VF squared is 5.26 times 10 to the power of 15. All right, getting there. We're almost done. All right, so now it's getting rid of the 2, the squared. And so the only way to get rid of the squared is to do the square root. What you do to one side there, you got to do to the other. And so I just left it in my calculator. So we get VF is equal to, all right, let's see. It is going 7.26. Oops, I'm going to run out of room here. It's a big number. Scientific notation. So we get 7.26 times 10 to the power of 7. And again, in our standard units, we got meters per second. And that is the speed at which our electron would be hitting the positive plate, given knowing the voltage, which again tells us our electric potential difference, the energy that's going to be released. All right, given the charge that we have. Oh, now we have B. Calculate the magnitude of the electric field. And again, our electric field, let's out from the positives, right? So we want to calculate the magnitude of the electric field at a distance of 15 centimeters. All right, so let's see here. So we want the electric field. So this is B. So we got the electric field. We're wondering, what else do we know? We know the potential difference of this situation was 15,000 volts. All right, the delta D. We know the delta D. The distance was, I believe, 15 centimeters. Which is 0.15 meters. All right, now we have a formula. Again, one of our formulas that we just came up with, where our delta V, potential difference, is equal to negative epsilon. Again, which should be a vector, or it is a vector. We're just usually dealing with magnitudes. With our displacement. All right, so our displacement is going to go right in here, our delta V right in here, and we can find our epsilon. Now again, in this situation, we see our delta D and our negative sign. And I'm going to go up in this situation. Again, look at the purple arrows. That is our electric field. And our delta D, again, our displacement is against that. It's in the opposite directions. And so when I substitute into our formula here, our delta V, nothing's going to change there. I got 15,000 is equal to negative, we want our epsilon, delta D, not only, I'm not going to put 0.15, but negative 0.15. All right, so again, those two negative signs as we had before cancel each other out. So essentially we've got epsilon times 0.15 equals 15,000. And so to get epsilon by itself, I'm going to divide by 0.15. And what you do to one side, you do to the other. And so those divide each other out. And so the strength of our electric field, that's all we're worried about too. That's why the sign really doesn't even matter, because we're just looking for the strength of our electric field. Let's see here. We get 15,000, ooh, big number, divided by 0.15. And I get the strength to be, got scientific notation here, 1.0 times 10 to the power of 5. And that is newtons per meter. Oops. There we go. All right, now, next up, another situation. I like this one. Two particles. A proton with charge Q. Again, the opposite charge of an electron, same magnitude. Different mass, though. We got 1.67 times 10 to the negative 27 kilograms. And an alpha particle with a charge and a mass are separated by an extremely large distance. Okay, so we got a proton and an alpha particle, both positive. Now, they approach each other along a straight line, so they're fired at each other essentially with speeds of v, 3 equals 3.0 times 10 to the power of 6 meters per second each. Calculate the closest distance that these two particles will reach. All right, so here's what we're going to do with this one, a little different. We're going to use a conservation of energy. All right, but we got three energies, sorry. Is that we're going to have kinetic energy for both particles. So this is our EK, let's see here, first particle. Let's say our proton there is particle number 1. All right, plus there's kinetic energy for our second particle, which I'll say is our alpha particle. There we go. And then initially we have some, we don't have any electric potential energies. Because, well, I guess we kind of do, because they are a distance apart. But I guess it's kind of like saying they're infinity apart. Well, number 1 here, because of this speed that they're being fired at each other with, we are going to have a change in our electric energy. And again, total is going to be up. So what's going to happen here is these two kinetic energies, these two particles are going to be fired at each other. Because they are repelling each other, though, because they're both positive, eventually that tension will, it's like pushing a spring together. You can only push it so close together. And in this case, we're going to find out how much energy is basically stored in that spring, or that electric energy. All right, so again, our first kinetic energy, any kinetic energy actually, we have m times v squared divided by 2. Now the change in the first kinetic energy, they don't have any final kinetic energy. All right, so we'll get to that actually. So we're going to substitute into our formula here. So for our first kinetic energy, we have a mass. Let's see here, of our first particle, which is 1.67 times 10 to the power of negative 27. Okay. Its initial velocity, it's being fired. They're both at the same speed here of 3.0 times 10 to the power of 6. But again, with this formula, you got to square it. All right, now then, divided by 2, can't forget that. I have room here. All right, plus we have our alpha particle, which has another different mass of 6.64, times 10 to the power of negative 27 kilograms. All right, our velocity here is, okay, same one. So 3.0 times 10 to the power of 6. And I got to square that, and again, divide by 2. All right, now our electric energy. All right, which is going to increase. All right, so our kinetic energy is going to decrease. And so we should put some negative signs. I will get to that. We'll put some negative signs on that. But again, our electric potential energy, we have our formula of K times Q1 times Q2 divided by the change in distance. These two are going to have. Well, it is delta D, so actually we're going to be looking for that is the net formula, but we're going to be looking for the change in the distance. All right, so that energy, we have our K value. All right, our charge on our first particle is a proton, so that's 1.6 times 10 to the negative 19. Just going to fit this in, it looks like. Q2, let's see here, an alpha particle, 3.2 times 10 to the power of negative 19. All right, over delta D, because we're looking for the change in our electric energy. It's going to be determined by the distance. Now, this all, because run out of room here, is equal to 0. All right, now, again, what's going to happen here, the change, is the kinetic energy is decreasing, right? It's being converted into electric energy. All right, so I got a minus sign here because the proton is going to lose kinetic energy. And I might as well just change this to a negative sign because our alpha particle is also losing energy. All right, so now a little calculator work. Yikes. Okay, so let's see what I get here. I got to take 1.67 times 10 to the power of negative 11. Times 10 to the power of negative 27. Then I'm going to take, then I'm going to multiply it by 3.0 twice. And then I got to take, multiply it by 10 to the power of 6 twice. And then divide by 2. So let's see here. Let's give me a second here. And again, it is kinetic energy. We're losing it because these particles are being fired at each other. All right, and let's see here. So we end up with, give me a second. So I end up with 7.515 times 10 to the power of negative 15. All right, this is big, so I might as well just shrink this right down. There we go. All right, subtract. Not subtract, really, it's adding, but this one's also negative. So I take my 6.64 times 10 to the power of negative 27. Then I'm going to multiply it by 3 twice because it's squared, and then multiply it by 10 to the power of 6 twice because it's squared, and then divide by 2. And end up with 2.99, let's see here, times 10 to the power of negative 14. All right, and then plus our K value. What was that again? I'm going to look at my formula sheet. I believe that was 8.99 times 10 to the power of 10. I just want to make sure. Let's see here. Oh, yeah, there it is. Okay. All right, so then I multiply it by 1.6 times 10 to the power of negative 19, then times 3.2, and then times 10 to the power of negative 19, and I get, let's see here, I end up with 4.6 times 10 to the power of negative 28. Oops, put a little exponent sign there. All right, and again, conservation of energy equals 0. All right, so, and I can't forget, this is where math's going to get tricky. I got the delta D in the bottom. Alright, so now, let's see. I'm going to put these two numbers together. Alright, and then it's going to be negative, so we got minus 7.515 times 10 to the power of negative 15 minus 2.99 times 10 to the power of negative 14. It's going to be a negative number, so then I'm going to move it over to the other side so it becomes positive. Alright, so that number, if I put them together, is 3.74 times 10 to the power of negative 14. I see a lot of math going on here. And again, over here on this other side, I got my 4.6 times 10 to the power of negative 28. And the delta D is in the bottom still. All right, now next up, anytime I have something equaling a fraction, I always like to create a fraction equaling a fraction so that I can cross multiply. All right, so I'm going to end up with, let's see here, 3.74 times 10 to the power of negative 14 times my delta D is equal to, well, 1 times 4.6 times 10 to the negative 28, which is just going to stay that same. Whew, we're getting there. All right, and then finally, this distance, let's see here. I got to get delta D by itself, so we're going to divide both sides by 3.74 times 10 to the negative 14. All right, do the same thing on the other side here. And so they divide each other out, and so our distance that these two particles being fired at each other from, I guess, an infinitely far distance away. So let's see here. Now we're talking about electroscopic particles here. And so our distance ends up being, I divide my two numbers here, I get 1.23 times 10 to the power of negative 14 meters. So that's, none of us are going to be able to see that with our eyes. And there we go. So there's just some different scenarios with dealing with voltage. Again, this is dealing with last example is dealing with the conservation of energy, where we had two particles, both had kinetic energy that were going to be turned into electric energy. All right, and that's why we have our negative signs because on the kinetic energy because they lost it, and yet the positive sign here because our electric energy went up as these two particles were sprung together because they're both positive. And then we had a couple examples of using plates, particles being fired across plates.